Alright, so as we start talking about the smart grid and we talk about electric reliability, power quality, things like that, we quickly start to realize is that we need to take a lot of measurements or a lot of readings from this environment so that we know what's happening in real time, so that we can detect problems, so that we can troubleshoot things. So it's not just important to know what's going on exactly right now, but it's really important to store this data long term so that I can look at trends, maybe intermittent problems. I can go back and look at these problems over time. And this becomes a pretty big problem if we look at our little right here. A modern electric grid is going to consist of all the things that it always used to. These traditional power plants. You're going to be collecting information from these power plants about how much power they're producing, things like that. You're going to be collecting data from houses, your customers, and even a small utility will easily have a couple 100,000 customers, and larger utilities have millions of customers. So instead of going and taking one reading a month to see how much power they used, these days you'd like to know how much power they used. How much power they used at what particular time. Some of the things that we're trying to do are demand-based pricing, so that you would charge a different rate, say for a customer to use power at night when there isn't as much demand, and you would charge them more power if they were using it in the afternoon, say when you were reaching your peak. The other thing that we're starting to do is we're starting to put all these renewables in the grid. And one of the interesting things is you can see that these are kind of out here where the houses and factories and stuff like that are. They're not really sitting next to the power plants. So your distribution grid starts to look different. You've got these solar farms feeding power back into the grid from different locations. And a lot of times you even have people putting these on top of their houses. So you have them feeding power back into the grid. Well, all this makes the grid tremendously more complex, and you have to start collecting data so that you can analyze this new behavior. These newer grids are things that haven't been operated for years. The old grid's been operated for years, and so we've seen the problems. We know how they work. We know how to design for them. We're starting to see a lot of new challenges with these new grids. And so collecting information and having historical data that we can analyze becomes very important. There's a word for this collection of data, this data measurement made at a distance, and it's called telemetry. So when we talk about this, we're talking about collecting telemetry. We're talking about measuring data from a distance. Now, when we collect this data, what we're really doing is we're going in at periodic intervals. We're asking for data from instruments on the grid. Well, this type of data is called time series data, and time series data is a sequence of data points typically measured at successive time instances spaced at uniform time intervals. So any kind of measurement that you're going to take from the computer is going to look like this, and it's going to look like some sort of a continuous signal, but in reality what it's made up of is discrete time measurements. So we're going to talk about time series data, pretty exclusively. That's what we're collecting. That's what we're concerned with, and you're going to get to know the intricacies of collecting and analyzing time series data. So time series data looks like a continuous signal. It's going to look like you've got all the data there, but in reality it's really made up of discrete time intervals, discrete measurements at discrete intervals. So this data collection, you've got instruments in the field, okay, instrument here, and these instruments, for our purposes are going to be things like electric meters, or very specifically here on the Palm Beach State campus, we have these meters installed, collecting information. And so, basically what this looks like is an instrument of some sort with a communications link and some sort of a data collector. So we're going to talk about how all this works. The data that you collect from the instrument, each reading that you might collect from the instrument is is called a tag, and a tag is any item of information that we collect. Okay, so for this meter, it might be the wattage, or watt hours, or it may be voltage. But each one of these things has to be identified with a unique tag. Okay, so each one of these is going to have a tag name, and a lot of times what you do is you put some sort of a prefix on it. So, it might be house whatever, house number, or customer number whatever, voltage, customer number whatever, wattage. But you have to come up with some sort of a unique tag naming scheme. Now these tags can typically be these tags can be of different types. Okay, they can be continuous. Most of what we're going to look at in labs and stuff like that is going to be continuous data, because that's what we're getting from our meters. Okay, so examples of this would be a voltage. Maybe you're reading a voltage. Maybe you're reading a flow. We're talking about electric grids, but maybe you're also distributing water, and you need to know what the flow of water was. Maybe you need to know the watts or the watt hours. A temperature or pressure would also be examples of these continuous signals. You also have discrete measurements in a lot of systems. So these discrete measurements indicate some sort of a state. So an example of this would be an on-off signal. Maybe you have a pump or a motor or something like that, and so you have a tag that tells you whether or not that motor is on and off. And then that tag could also be associated with a motor. You could also cross-reference that with, say, the amps to the pump. So maybe you would look at this motor or this pump, and you would graph whether or not it was on and off and how many amps it was pulling. Other examples would be auto and manual. Maybe you've got something something that keeps some sort of a set point. You would maybe put it in automatic mode, or you would put it in manual mode. Well, that's something that you'd like to know if you were going back and troubleshooting. If the thing wasn't operating right, and you had it in automatic mode, that would mean that the automated controls weren't working right. Although if it was in manual, it would mean maybe the operator just hasn't set it properly. Also, things like step 1, 2, and 3, or something like that, some sort of a sequence that a piece of equipment might operate in a certain sequence, and so it might have some sort of a discrete output that it would tell you what step it was in. So that's talking about the instruments and the tags and the different types of tags. Now, next we're going to talk about this communication link and how you go to ask for the information. There's two main ways that you're going to get information from these instruments, and the first one is polling. Okay, so with polling, what you do is you send a request to the instrument. You say something like, please give me the voltage reading. And then you're going to get back a response, and it's going to say the voltage reading is 120 volts. So whenever you do that, whenever you send a request and you get a response, it's known as polling the instrument. The next thing would be exception reporting. Now this can sometimes be a much more efficient way of doing things, and the way this works is you send an initial request and you say, okay, Mr. Instrument, I'm interested in knowing whenever the voltage changes. And then after that, you're going to get responses whenever the voltage changes. So you send an initial request and you get back these responses periodically. So what might happen with this instrument is it may just send you the instrument back once a second. It may just always send it. It may only send it if the reading changes, and this would be reporting by exception. So it would say, okay, the voltage is 120. Unless you hear back from me, you can assume this reading is always going to be 120. Now, one of the things that you'll do in the real world is that, of course, you don't want to just assume that the reading stayed at 120 and that instrument's still alive. So you might have some sort of a timeout that says, okay, Mr. Instrument, I'm interested in knowing about the voltage. Give it back to me every second that it changes. But if it doesn't change for an hour, then send me a response just to let me know you're alive. Send me the reading. So this thing may sit there and read 120 volts all day long, but every hour it would let you know with a response that it was still alive, it was still measuring, and that indeed the voltage had not changed. Alright, so when we make these requests from the data collector, whether we're polling or reporting by exception, we have to know what language to speak, okay? So in order to communicate with any of these instruments, we have to have a common language, and this common language is known as a protocol. Alright, so there's basically two different types of protocols, or this is how I'm going to choose to break this down. And they are open protocols. Okay, so an open protocol is one where the specifications publicly published. Okay, so all the details of how to implement this are made public, and they're freely available. And so anybody who creates an instrument or who manufactures an instrument would be able to use this protocol. They don't have to pay any licensing fees or anything like that. So it's an open protocol. The really nice thing about this is if you're a smaller manufacturer, you can use these open protocols. They're very cheap to use, and it's very nice for you to be able to go to your customer and say, I speak this open protocol. Now, the other thing you're going to find is proprietary protocols. Okay, so these are vendor specific. They may only be available for that vendor's equipment, so they may not be interoperable. You may be stuck using this particular protocol, this particular vendor, and it may limit the way that you can talk to this piece of equipment. Oftentimes, if third parties want to use this protocol, they're required to pay a licensing fee. Sometimes the vendor doesn't even make that option available to you, and I always call this the vendor tax. So an example of proprietary protocols may be you would buy a meter from GE, and it would speak some sort of a GE specific vendor proprietary protocol, and then you might also have some Siemens instruments that use a Siemens protocol. And so the bad thing is that you have to have a way to talk to the GE instruments, and you have to have a way to talk to the Siemens instruments. And versus the open protocol would be much nicer because they would both speak the same protocol. It wouldn't matter whose instrument you had used, you would still use the same protocol to talk. So this is one of the things that you run into, and one of the things that I want you to be aware of. Okay, so just for a little recap now, we've talked about protocols and languages and the data collection process. So you've got a data collector. It communicates via this protocol to an instrument. Commonly it'll either poll or have some sort of exception reporting to get the information. When you communicate, you're always communicating about tags, okay? And tags always have a unique name, and a tag is just one item of information that you're going to collect the time series data for. They can be continuous or discrete. So continuous would be things like voltages or things that vary, a number. And then discrete would be discrete things like on or off or specific states, very well-defined discrete measurements. Time series data, everything that you collect is going to be time series data. And we've talked about time series data just being a signal that you're collecting through periodic measurements. And of course, all of this relates to the smart grid because telemetry and data collection and understanding what's going on in this much more complicated and complex environment becomes very important.